Today we're talking about atomic theory. Now we've done a bunch of atomic theory in the past. We're going to kind of keep going. If you remember from grade 11, we said that the Bohr theory was not the currently accepted model, but we didn't say what was. So now we're going to get to that currently accepted model. Let's quickly remind ourselves of how we got there, though. John Dalton said that all atoms are made of solid spheres that were indestructible until somebody came along and discovered the electron. Okay, well now we have negative charges and positive charges. Let's call it a Rosen-Bunn model. And then we tested the Rosen-Bunn model, by Rutherford did, and found out that no, Rosen-Bunn doesn't really work. It's a nucleus. So now we had more of a solar system. And then Bohr came along and said that it's not just a simple nucleus in the middle, electrons around it, but those electrons are actually in energy levels, specific energy levels. And that was a big thing in grade 11. Now, if we take Bohr's theory, you don't need to write this down because we're going to be moving on from that. But if you look at Bohr's theory and look at some of the other things that it means that at the higher energy levels, the electrons are moving faster. That's how the more energy plays out, faster speed. It also means that we should be able to figure out where the electron is and how fast it's going. Is it in the first energy level, second energy level, third energy level? And then if it is in any one of those, this is how fast it must be going. It also means that if it's a circular orbit, we can figure out a really a very accurate measurement of the radius, and that radius shouldn't change because as soon as it changes, we would have to change the speed. The problem with that is, as they started looking for those kinds of bits of evidence, they ran into some problems. And one of the problems with Bohr's theory was the order of fill in the atom. That we can say, for example, we can see that in the third energy level, third orbit of Bohr's model, there's room for 18 electrons, but we fill it to 8, and then we move on to the fourth one, and then we come back and keep filling the third. So Bohr didn't understand how the order of fill went. Second thing is that, man, this is a big one, kind of, is that Bohr's theory only works for hydrogen. As soon as you get into more than one electron, like every other atom out of the 115, 116 that we know about on the periodic table, Bohr's theory doesn't work. So as a concept, it works pretty well. Electrons moving to higher energy levels, falling back down. As a concept, it works well, but as a detailed model of the atom, doesn't work so well. So all of that's in the past. We're going to move on. This is where we want to start keeping track of what's going on. So if you're writing anything down, this is where you want to start. Atomic theory for us is going to be quantum theory. And quantum theory is the currently accepted model of the atom, but creation being what it is, as amazing as it is, we can never get the perfect picture of what it looks like. So our understanding of the atom is always growing, always changing. It uses something called wave-particle duality. Now for us, that may not mean a lot, but the short version of the story is that once you get very, very small particles, the rules change. Now that idea was revolutionary at the time because we like to take a big thing and scale it down to a small size, or take a small thing and scale it up to a large size. Wave-particle duality says at a certain point when you scale it down, the rules change. You can't use regular rules of physics. So once we started to accept that, and then we could move forward. Here's the other problem. Here's the problem that for us is going to be a big deal, is that quantum theory is a very mathematical model. And what that means is it's very difficult to draw a picture and to say this is what the atom looks like. We can write equations for it, and I'll show you an equation in a minute, but that's the best we can do. So for us to turn that mathematical model into something physical that we can draw and show pictures of will be a challenge. Just a heads up before we get there. A few other framework things that we need to know. Number one, something called the Heisenberg-Uncertainty Principle. And the Heisenberg-Uncertainty Principle says that that whole business that Bohr said we can know the electron is here, we can't. Whatever we do to figure out where the electron is, will change it. So this principle, Heisenberg-Uncertainty Principle, was not real popular at the time. A lot of people mocked it. Remind me to tell you the story about Schrodinger's cat. But it was basically somebody effectively mocking the Heisenberg-Uncertainty Principle. They were saying things like, well, we don't know where the electron is, so it could be anywhere. It could be on the moon. How did it get there? We don't know. Well, seriously, what would happen if all your electrons decided to go to outer space? Okay, bad day. Anyhow, what we are able to do is predict fairly accurately, we think, where the electron probably is. We can't have 100% certainty, but we can get a pretty good idea of where the electron should be. So that's the best we're going to be able to do. We'll talk about probability distribution. And what we're going to do is we're going to give that probability distribution the name orbital. Really important right now, the orbital is not the same as an orbit. It is not a circular pathway. It's an area, maybe a volume of space where we're likely to find the electron. We're going to spend most of our time talking about atomic orbitals, the orbitals that exist, the places where we're likely to find electrons in an atom. We will try and transfer that into molecules, but we're going to have to cut our discussion a little bit short because once you're into molecules, things get a little bit weirder. So we'll just sort of set it up and let somebody else deal with it another time. But if we're talking about small particles behaving as waves, then our orbital, our different energy levels, refer to different waveforms. Let me show you some pictures of different waveforms. So here's some pictures of waves. And if you look, each one of these things fits in the same overall space, but in a different form. Okay, kind of simple. Those waveforms, once you start talking about electrons, represent different shapes of where the electron might be. So some examples of that. We can have something called an s orbital. Now we'll deal with exact shapes and not exact shapes, but we'll deal with shapes and the names a little bit later. So for right now, you might just want to have s orbital. It's spherical. All right, it's hard to show that on a two-dimensional screen, but it's spherical, shaped like a ball. You can have p orbitals, and these p orbitals are, number one, shaped like, I don't know, propellers, and number two, they're in different orientations. So I can have one going left-right, I can have one going up-down, and I can have one going out of the screen toward you and back to the screen behind me. I can have d orbitals, and d orbitals, again, have different shapes. Now, one thing I don't like about this picture, but I could not find a better picture, you'll notice that these d orbitals, there's 4 lobes, and there's different colors. I would actually like them if they were all the same color. You do not need to draw these. We're just going to know them as d orbitals, and eventually it's important that there's 5 orientations of those, and they're all the same energy. There's also f orbitals, but for us, as long as we know the letter, that's it. All right, so going back to atomic orbitals, we know there's different shapes of probability. There's also, because of that waveform, only certain wavelengths or only certain energies will even be allowed. So if I go back to this picture, not back, but if I look at this picture, you'll notice that I can fit 2 different waveforms into the same full length. But if either one of those waves were a little bit shorter or a little bit longer, wouldn't fit. Well, if each wavelength represents a different energy, only certain energies are even possible. So now we have our specific energies falling into our lap. We don't have to start with that as one of our statements. We're going to end up describing the electron, the energy of the electron, as a series of numbers. And those numbers, because it's a mathematical model, those numbers are going to be used to, well, solve an equation, for one thing. Don't write this down. Whatever you do not write down this wave equation. But here it is. So the wave equation is very, very complicated. And this is a fairly simple one in a lot of ways. But each term, so starting from the left and working our way right, the first bit tries to describe the electron, the probability of finding the electron in the x direction. Second one is probability of finding the electron in the y direction and z direction, and so on. So now we've got our 3 dimensions. The other terms describe the mass of electron, the radius that it's likely to be found in, a bunch of other things, and so on. Not going to need to know it, not going to need to solve it. Just want to impress you, well, not with my ability, but with how big this thing can be, and therefore how complicated quantum theory can be. What we're going to do, though, is not use it as a theory. We're going to use it as a model. What does it look like? How does it help us? Okay? In order to solve that equation, I know it doesn't look like a lot of spaces for variables, but you'll need 3 quantum numbers. We'll actually have 4, but we'll talk about that in a moment. So here are the quantum numbers. You want to know these. You don't need the equation, but you need to know the numbers. First one, we're going to give the symbol n. Principal quantum number. It's a lot like what we used to have for the energy level, or the orbit number in Bohr theory. It's a really good way of describing the energy of the electron. So an energy with n equals 3, sorry, an electron with n equals 3 has more energy than an electron with n equals 2. It's kind of like the orbit number, as I mentioned, and it also, even though we're talking probabilities, we don't know where the electron is for sure, smaller values of n, those electrons are more likely to be closer to the nucleus than larger values of n. Values are the counting numbers, 1, 2, 3, 4, and so on. Next number is L. Now I always write it as a script L just to make it more clear, but it doesn't have to be. It could just be a print L, but that looks like a 1 or something else. That's the orbital number. Now it's got a couple of other names, sometimes called the secondary quantum number. I like to refer to it as the sub-energy level. It will also tell us the shape of the orbital. If you think back to those pictures where we had p orbitals and s orbitals and d orbitals, those letters actually correspond to different values, numerical values for L. The value depends on the value of n, and what I mean by that is L can be 0, 1, 2, 3, or up as high as n minus 1. Always starts at L equals 0. We'll make more sense of that in class, don't worry. We also use the letter value. Sometimes we do, sometimes we use the numbers. We'll figure it out when we use letters, when we use numbers, but those letter values that you saw a few minutes ago, those correspond to the values of L. Magnetic quantum number. So now we're under our third quantum number. This is the third number that's required to solve the equation. The magnetic number, m subscript L, which I normally refer to as m sub L. It tells us the orbital orientation. Think about those p orbitals. One was along the x, one was along the y, one was along the z. Left, right, up, down, in, out. Different orientations means different values of m sub L. The number of possible values that you have will tell us the number of orientations that we have. And the values are going to run from negative L up to positive L. So in other words, let me just go back to there. If L is equal to 1, negative 1, 0, positive 1. Thought I had that on there. I said there was 4 numbers, 3 were required. The last one is a spin number, m subscript s or m sub s. And that recognizes the electron with its particle property. So it's not longer moving as a wave, but it's a particle that has a spin. And it can either be spinning clockwise or spinning counterclockwise, depending on a few things. It also will allow electrons to form pairs, because we know they pair up. Think about Lewis diagrams. Electrons had to be in pairs, but also have a unique set of quantum numbers. So same energy level, same sub-energy level, even the same orientation, but opposite spins. So now we have 2 electrons, and they still have 2 different quantum numbers. The values used are plus 1/2 and minus 1/2. And it's a little bit arbitrary, just so that we have a direction and a different direction. We'll talk about more how to use these numbers, how to set them up in class. For right now, it's important that we understand what the numbers are, what the limits are, what they're called, what they mean, and then we'll jump into using them in class in the next day or so. Talk to you later.